Everybody. I'm going to go over this worksheet. This was the review of what we did the week before break, and I just want to make sure that everybody is on the same page with going over these problems. So the first two questions, what is a permanent magnet and what is an electromagnet? Permanent magnets don't change. They can get a little stronger, they can get a little weaker, but they will always have the same magnetic field. North will always be where north is, south is always where south is, and you can't just turn it off. Whereas an electromagnet is only magnetic when there's current. So if current is running through the wire, it will be magnetic. And you can shut it off just by turning off the current. I'm going to go through questions 3 and questions 5 next, and I'm going to do both of those together because they're all about permanent magnets. And I'm going to change this a little bit so you can see the board a little bit better. So I have on the first one, on number 3, I have a north over here and a south over here. When you're drawing magnetic fields, you always draw from north to south. You don't need a ton of field lines. 2 is just fine. So you've got from north to south. If you did the magnet station on the Friday before we were on online school, that was the 13th, you had an opportunity to put a compass around a bar magnet and see what it did, and it aligns itself with this magnetic field. Okay, so the next one, number 5, we have 2 magnets. We've got a south here, and we've got a south here, and a north here, and then again a south and a north. And we're looking for the magnetic fields between those 2 magnets. So again, north always, or magnetic fields always go north to south. And those 2 magnets will end up attracting. All right, so I thought I hit pause. Okay, so now let's do 2 and 4, which are both electromagnets. So we always have a hard time drawing the magnetic field around wires. So this would be an electromagnet, current running through a wire. And indicating direction is always a little tricky. If it's going to the right, we just draw it to the right as an arrow. If it's going to the left, we draw it to the left as an arrow. But if it's coming perpendicularly out of the page, that's a little harder to draw. So again, we think about an arrow, and if an arrow is coming towards your face, what you're going to see is the point of the arrow, just like you're seeing the tip of my pen. And we'd represent that with a dot. So that would be coming out of the page. If instead it was going into the page away from your face, what you would see is the back end of the arrow, which would be like the feather part, which we would indicate with an X. So on question number 2, where it says describe the direction positives would move if the picture below represents current in a wire, the positives are going to move out of the page. So that's how we would indicate that. And then to draw the magnetic field that would exist around the wire, we use the right-hand rule. So we take our right hand, you got to make sure it's your right hand. Your thumb points in the direction of the current, so it's going to come out of the page towards your face. I can't bend it all that well, but there we go. So out of the page towards your face, and then your fingers represent the magnetic field as they curve around that wire. My fingertips are like arrowheads. So the direction that my fingertips are going is the direction that the magnetic field is going. So when I draw this, it's going to be a circle with an arrow on it pointed in that direction. So that's number 2. Number 4, we've got 2 sets of wires. We've got a wire that's connected to plus here and minus here, and another wire that's connected plus here and minus here. These pluses and minuses are battery terminals. So for this wire, that's hooked to the negative side of the battery. This one's hooked to the positive side of the battery. This one's the negative side of the battery, the positive side of the battery. So those pluses and minuses don't really represent charge. They represent the positive side of the battery or negative side of the battery. The positive and negative sides of batteries, they don't do anything. They don't attract, they don't repel, they just sit there. So if you're not sure about that, take out the batteries in your remote and try it. They won't. They'll just hang out. So these wires won't attract or repel because of these pluses and minuses. They attract or repel based on the magnetic field that's in between the 2 wires. So we need to figure out what that magnetic field looks like. And in order to do that, we need to figure out current direction so that we can use our right-hand rule. So current always travels the way positives would go if they could. So positives want to go towards negatives. So my current is always going to point towards the negative. And that tells me what direction my thumb is going to point. So my thumb is going to go in the negative direction. And sometimes it's easier to use a pen to stand in for your wire with the current. So my thumb points towards the right, and my fingers are going to wrap around that wire, creating that magnetic field. Now this is exactly the same magnetic field that was over here. So my fingers are curving around in that direction. The field is, or the current is coming towards your face. But now I'm tipping it sideways so that it's a circle, but it's coming out above the wire and going into the page below the wire. So another way to think about that is my fingertips are like dots, so the arrowheads, and my knuckles are like the X's. So my fingertips are above the wire, so that's where dots are going to be. And it doesn't matter how many of these you draw. I'm going to draw 3. And then I have X's underneath the wire. So it's coming out of the page up here, going into the page over here. So it's like a loop circling around that we've chopped off halfway so that we're seeing it come out over here and go in over here. This wire is going to go the other direction. So the current is traveling this direction, so my thumb has to point towards the negative. I've got knuckles on top and fingertips underneath my wire. So I have X's on top and dots underneath. So now, what are my wires going to do? If you think of dots as being north and X's as being south, in between this wire, I have south and south, or X's and X's. Those are exactly the same magnetic field. And if you have the same, they're going to repel. So these 2 wires are going to push apart because the magnetic fields here are the same. So they're going to push those 2 wires. It's going to repel. To do the last questions, I'm going to share my screen with you and we'll get to the math. So this is figuring out magnetic field strength and magnetic field force. Oops. All right, so we've got number 6. The magnetic field strength, 2 meters from a wire, with 10 amps of current running through it. So magnetic field strength is B. That's what we're looking for. That's our unknown. We are 2 meters from the wire. That's R. So kind of like when we were doing the force of charges, R was our distance. Same thing is true here. So in the K, Q1, Q2 over R squared. And then we've got a current, that's I, of 10 amps running through it. Our equation for magnetic field strength is 2 times 10 to the negative 7th, that's just a constant, times I over R. So this constant here, so this constant right there, so 2 times 10 to the negative 7th, is a lot like our K that we had in K Q1 Q2 over R squared, that 9 times 10 to the 9th. It doesn't change, it's just a constant. So we plug it in, we've got 2 times 10 to the negative 7th times I is 10 amps, and then divided by R is 2 meters. It's going to give us 1 times 10 to the negative 6. And our units of magnetic field strength are Teslas. To do the last question, which you already got a preview of because I forgot to erase it before, we have the magnetic force. That's what we're looking for in this one. That is a question mark. Felt by a 2 meter long wire. Length of the wire is 2 meters. It's got a current of 5 amps. And it's in a magnetic field of 4 Teslas. Our equation for force is Bill. So the magnetic field strength times current times length. That's going to be 4 times 5 times 2, which is 40. And the units on that are going to be newtons because our force is always newtons. Please contact me if you have any questions. I'll do Zoom meetings during the 1 to 3 Gator time, and I'll also do Zoom meetings in classes from this point forward now that I know how to do this. And I hope that you're doing well, staying healthy, social distancing, washing your hands, all that kind of good stuff. I miss being in class very much, and it's good to connect with you.